Alright, so this video is going to be about the eigenvalue step of the eigenvalue analysis and linearization, saga of videos. So in this video, what I'll be doing is I'll be describing the process of eigenvalue analysis, showing you how it's done, and kind of going through a couple examples to just get you started on thinking about it and letting you know how we're supposed to do it. Now we're just going to do a couple examples of eigenvalue analysis and do an introduction on how to do it. So we're just going to suppose that we already have a linear system to practice the analysis with. So first things first, how do we even calculate our eigenvalues? Our eigenvalues will be represented by lambda plus and lambda minus, as we will get two results from our equation shown. This is where the positions of the coefficients in the linear system come into play. Those coefficients are plugged into our eigenvalue function. So it does matter where you pull your coefficients from as to how the original linear system is arranged. Now, what exactly happens when we plug in our values? Well, once you work out a solution from our plugged in values, you will receive your lambda plus and your lambda minus from the function. And depending on their signs, your systems will have different types of behavior. So when lambda plus and lambda minus are greater than 0, the equilibrium at 0, 0 is a source. And then when lambda plus and lambda minus are less than 0, the equilibrium at the origin is a sink. And finally, if lambda plus and lambda minus have opposite signs, the origin is a saddle. All these terms are fairly new to you, so what I'm going to do is I'm going to actually show you what these look like. First, I'm going to show you what a source equilibrium looks like. This is when lambda plus and lambda minus are greater than 0. It's like a repelling origin. So the source is when all of our phase lines for our phase plane are pointing away from the origin itself. This makes it unstable. Then we have our sink equilibrium, and this is where both lambda plus and lambda minus are less than 0, and as you can see, we have a stable attracting type equilibrium, so that means that all of our phase lines in our phase plane point towards the origin instead. That is our sink. And then we have our saddle equilibrium, and this is a little bit different. I try to consider this as like a neutral equilibria, considering it's not really attracting or repelling, because you have two directions. You have one pointing towards the equilibria, and then you also have one pointing away from the equilibria, so it's neither attracting nor repelling. So this is what a saddle looks like. It's kind of like both, and this is when lambda plus and lambda minus have differing signs. Well, what happens whenever our eigenvalue equation has a negative under the radical, so our lambda plus or minus isn't a real number? Well, when this happens, we take the imaginary number out of the radical and think of our expression as a plus bi equals lambda plus or minus, where a and b are actual real number representations, and then the I is our square root of -1, which comes from the radical. Well, when we work this form out and have everything simplified down to the point where we have our imaginary term and have our expression a plus bi, we have a couple rules that determine the behavior of the equilibrium. If a is greater than 0, then our equilibrium is an outward repelling spiral. If a is less than 0, then it is an inward attracting spiral. And if a equals 0, our equilibrium is actually a circle. So to practice this, I think that we should do a couple examples. So for our first example, we're going to work with a 2DE linear system, where we have dx dt equals negative 2x minus 3y, and we have dy dt equals 3x minus 2y. So what we're going to do first is we're going to figure out what our different terms are for our eigenvalue analysis equation. So we can definitely see from this that it's already laid out in the way that it should be to find our a, b, c, and d. Our a is equal to -2, our b is equal to 3, our c is equal to 3, and our d is equal to -2, and then actually our b is equal to -3. Make sure you watch your signs. And then now having those values, we can plug them into our eigenvalue formula. So for our first bit, as you remember, we have a minus d, which is -2, actually it's a plus d, so it's -2 plus -2, plus or minus the square root of a minus d, so that would be -2 plus 2 squared plus 4 times b times c, all over 2. So then when you work this out, you would get negative 4 plus or minus the square root of negative 2 plus 2 is 0, so 0 squared is 0. So you would just have 4 times negative 3, which is equal to negative 12 times 3, which is equal to negative 36. And then you would have all of that over 2. So then what you can see is that we do have a negative under our radical. So what we're going to do is we're going to write that this is equal to negative 4 plus or minus 6i all over 2, which is also equal to negative 2 plus or minus 3i. So as you can see, we definitely have our a plus bi arrangement here. So with that, we can look at it and determine our equilibrium behavior. As you can see, our first term for a is negative. So since a is less than 0, what we have is an inward spiral. Alright, and then I think we should do a little bit more practice, but this time with perhaps a simpler example. So we have where dx dt equals 2x and dy dt equals 2y, and that's our 2DE linear system. So we can go ahead and start off by writing our eigenvalue parts, which are a, b, c, and d. So then you have a equals 2, as you can see, since the x term is 2. Since we don't have a y term for the first equation, our b equals 0. Our c equals 0 for the second one because there is no x term, and then our d equals 2 for our y term. So then once we have that, we can go ahead and plug into the eigenvalue formula. So our lambda plus or minus equals a plus d, so 2 plus 2, plus or minus the square root of a minus d, so 2 minus 2 squared, plus 4 times b times c, so 0 times 0, all over 2. So then once you have that, you can go ahead and simplify. So you have 4 plus or minus the square root of 0 plus 0 all over 2. And then you know that simplifies to 4 over 2. So our answer for lambda plus or minus is positive 2. Since we only have one value that represents both lambda plus and lambda minus, what we have is that 2 will just represent both. Since lambda plus and minus are greater than 0. That means that we have a source. But now what do we do if we have a nonlinear system instead of a linear one? Well, we can go ahead and linearize it using partial derivatives, which you learned about from our previous video. This will get us a linear system that's an approximation of the nonlinear one, and then we can do the eigenvalue analysis on that approximation to classify all of our equilibria this time instead of just the origin. Alright, and that's eigenvalue analysis. In the next video, I'm going to describe how you linearize a nonlinear system into a linear one so we can perform eigenvalue analysis. So good luck with that.